Good afternoon, everybody. We have a talk here about computational intelligence, how that can be used in a very useful way to model organizational learning. And as this is a remote presentation, I will also show our pictures. And I will do the first part, and July will do the second part with some more details about organizational learning approaches. But this is the context as a whole, contents. I will briefly introduce the idea of multi-level organizational learning with feed-forward learning from individual to organizational levels, or feedback learning the other way around. And then I will explain how computational intelligence is a useful means to be used in such cases, and in this case, especially the idea of self-modeling networks, where you can easily model adaptive systems, adaptive networks, but also even the control over adaptation. And we will just show you how you can use that to model a rather complex type of learning, what is the organizational learning. And especially July will do that, and then you can see how individual mental models in an organization can be aggregated to shared mental models, and that you can have control of such aggregation by a separate control level in the network. Most of the material is also coming from two books. One book that has recently come out in January. The first one on mental models and how you can model their dynamics, adaptation, and control, all three different manipulations actually of mental models. And the next book will come out perhaps the end of this year. Officially, probably it will have year 2023. And that's completely focusing on organizational learning and how you can model that. Also together with Anja Viviora from Management Science in Brisbane. So let's start. Multi-level organizational learning is what you can do in an organization to have knowledge not only in individuals, employees who can leave, of course, but also at the level of the organization, so that you have a more stable source of knowledge. So that means that individuals, your own employees in an organization, they can learn themselves and from each others, and they can develop knowledge in this way. But you want to also make a form of representation of that knowledge on the level of the organization, so that other employees can learn from that. And also, even if the original employees have gone, then still the new employees can also learn from that. And that learning is the institutionalization, it's also sometimes called, of this individual knowledge to in an aggregated form on the level of organization. That is called feed-forward learning. And then learning from that by individuals, it is called feedback learning. You can also do this with an intermediate level of teams. Maybe I can tell a little bit about advantages. There are efficiency advantages, because if you get the knowledge at the level of the organization, and it becomes very easy that any employee can learn from that. Of course, you could also let all employees learn from each other, but then you have kind of n² time of interactions that's not so efficient. And also, when employees leave, it's more efficient if you have it at the level of the organization. And also the quality can be better, and also the safety can be supported by that. So that's the general picture, but what I already told, you can also have an intermediate level, a level of teams. Then you can, similar things, teams can also learn from themselves, or within themselves, or from each other. And you can have then feed-forward learning from the individuals to the team, and feedback learning from the teams to individuals. And the same you can still do on the levels teams and organization, that you do feed-forward learnings from teams, and then also feedback learning from other teams can learn from their colleague teams. So this is roughly the picture what you can often see in the literature about multi-level organizational learning. And that's also what we will follow in our computational approach. So this is a nested structure of cycles. If you look well, you see one cycle here and a cycle around that one, and then a cycle again around that one. So it's a nested form of cycles. So it can be a rather complex type of process. And also with these teams even also can have more complexity. So let me first tell something about the idea of mental models. Kim's paper in 1993 is a very well-cited paper. Thousands of citations can be found to it. And what he says is that organizational learning depends on individuals. They improve their mental models of how they do their tasks, such things. And then making them explicit and is then crucial, because then you can develop shared mental models that can be shared with different employees. And that makes that you get knowledge independent of specific individuals. And mental models is in most cases where most of the knowledge, most of the expertise, know-how, know-why in an organization can be found. So that's why the mental models are considered in that type of literature. So a mental model is in fact a kind of relation structure. You suppose in the world there are some processes, for example, the workflow in an organization. Then you can have steps like after this that will come, and then in your mental model you have counterparts in the form of mental states, and they have the similar relation, similar causal relation, that this will follow that one. So that's the idea of a mental model. So that's a relation structure. So just like nodes and arrows, you can say causal influences, like in the world, can also be found and used there to describe processes in the world. So that's the idea of mental models. We have made, and especially this first book that came out in January this year is completely based on that, focusing on that. We have designed a cognitive architecture where you can use mental models, and that describes how you can use them by just running internal simulation of a mental model. But you can also learn them by adaptation of them, or forget them even, that you adapt it that it becomes weaker. But you can also have control of this adaptation, because that is very important. You don't learn just any time. You just learn from really initiated actions, for example, and not at other cases. So you can, the idea that learning is always constantly taking place is not a realistic idea. You need control to describe that you do it sometimes and other times you don't do. So that's why we have a three-level architecture, cognitive architecture, with these three different types of processes, all three involved. So this is internal simulation, learning and forgetting, and control of use, learning and forgetting. And this is then a relational structure, this kind of substructure in your total model. You can do adaptation of these relations, and you can control this adaptation of these relations. So that's the general idea of this architecture. That's also, we also were able to use that in the modeling of organizational learning. So the idea for the modeling approach that we use is that we use a network format. We call it the temporal causal network, because we assume that we follow causal relations, causal effects. And we do it in a dynamic way. It's the temporal side is also included there, addressed. So there is a network has connections, has nodes and connections. Nodes are also called states, because nodes have values that vary over time. And there are also weights of the connections. The connections are not absolute 0 or 1, but they can have any real number value as weights. So, and you need something to aggregate different impacts, because you can have different arrows to one state, y, and for that we use combination functions. And finally, for timing, we use speed factors for every state, so that you can give states timings that are just different, and you don't need to assume that they are acting in kind of synchronous way, because you can just give them their own way of processing. So these three types of characteristics, network characteristics, you can call them, of these different types, they define a network model. If you specify them, you can do that in table format, then you have your design of a network model. But to run it, there is a canonical difference equation, where all these elements can be found back. The omegas are here, the functions are there, and the speed factors are there. And this runs it, and this is a very powerful type of difference equation. For example, if you have a network of 100 nodes, which is quite normal, it's not so exceptional, then in the dedicated software that we have, automatically 100 instantiations of this canonical difference equation are created, and they are run by the software. So actually what you get is finally a system of 100 coupled difference equations, and they are just processed. But the specification is just in certain tables of these network characteristics. So you don't need all these technical mathematical details of even computer science details. You don't only make the tables. So this is a first book about these types of networks. You can see it here. That's from 2016. But already 4 years after that, there was a new book where also adaptation was addressed in a better way. And that's what I will tell about now, because that makes it still more clear, the form of computational intelligence, which is often about adaptation and learning. So networks can be adaptive. And that means that some of the network structure characteristics change. Well, we had these three types of them. So you can have change in connection weights if you want to change connectivity characteristic. For the aggregation, you can also change combination function, or you can change parameters of such functions. And then you have, for example, changing excitability thresholds. We will see some examples of this for the organizational learning level, because these things are very relevant for that domain to model it. And of course, you can also have changing speed factors. So that's the idea, but usually if people use network models and then you want to change them, they write a program to change the characteristics of the network. But that's a kind of hybrid type of modeling where you have a network model and then a program to describe the adaptation. Well, that's what we have developed in a different way. That I will show you by a metaphor type of form how you can do that. Suppose you have this picture, and you can also say, well, I put this picture within the picture. Then this is called, also if you look on internet, you can find many examples of this. That's also often called self-modeling, a self-model. So this picture is called a self-model. And that is actually what we want to do with the networks as well. We want to make a small picture of the network within the picture. You can even repeat that. Then you have a second order self-model, while the other one is called then the first order self-model. We will see that also in the network area. So how do we do that? How can a network model itself? Well, by adding a self-model to it, like in the picture, a subnetwork with states representing network structure characteristics in this case. And that goes as follows. you can have a net self-model for connectivity, for aggregation or timing. And this is an example. Suppose you want to have a self-model that covers a connection weight and a function parameter and a speed vector. Then you just add extra nodes, extra states in your network, and you connect them to the rest of the network. That is how it works. These are called self-model states. They are just a way of copying parameters to variables. But in this case, the variables are not arbitrary, they just also network concepts. That's a special thing here. So there is then a new book in 2020 where this approach has been worked out in detail in many chapters, and with software that also supports that one. So how can we, going back to the cognitive architecture for mental models, how can we model that as a self-modeling network? Well, it's not so difficult. We have just one network level where with the base network, where you have the mental model as a subnetwork. Then you have a first order self-model of the mental model, that is the adaptation. If you change the self-model, then therefore the characteristics are changing. And you have second order self-model for the changing of the adaptation. So the control can be modeled by repeating that construction. So therefore we not only use the first order, but also the second order type of self-modeling. So that's what we also have used to model the organizational learning. A very simple example of this, for example, if you would have a mental model with 3 states with connections, and then you, for this connection, you want to have it adaptive, then you have a state for that called W state. And as soon as this changes, this is also used to process the base level. But also this can be controlled by, for example, its speed is controlled here, or in this case, a form of persistence is controlled of it. So this is how it works then. So this is a good moment to shift to the real cases that July will describe.
Thanks, Jan. Hi, I'm Gülay, and I will try to give some concrete examples of our work. This is the picture for feed-forward and feedback mechanisms of organizational learning. We have individual and organizational levels, and sometimes there are group or team in intermediary levels. This arrow is for the feed-forward learning. The meaning of this is from individual to organizational learning. Individuals create the shared mental model with the help of feed-forward learning. And this arrow is for feedback learning. Feedback learning is the learning of individuals from their organizational shared mental model. This is an intubation scenario case adopted from a previous research. This is a complex scenario, as you can see from the picture, the model picture, but we used only a part of it to make things clear and basic. This is for a doctor's mental model, and this is the nurse's mental model. Doctor has different base level mental model states, and nurse also has, but we use only 4 of them for the intubation scenario. These are the explanations. The first task is preparation of intubation equipment. The other one is preparation of drugs, then execution of pre-oxygenation, and the last task is for preparation of the team for intubation. These first 2 tasks are mainly held by the nurse, and the last 2 are mainly held by the doctor. That's why the nurse is responsible for the beginning of the job, and the doctor is responsible for the last part of the job. We use representative names, basic names for these tasks to make these things generalize. We have task A, B, C, and D, and we have person A and person B, and also we have organization. In the base level, it is the basic skeleton of the model. And in this level, we have mental model states of person A and also person B. Person A represents the nurse. That's why A is responsible for, mainly responsible for the beginning of the job. And A doesn't have knowledge for the last task, task D. That's why there's no connection from C to D. And doctor is responsible for the ending of the job, the finished part of the job. That's why the person B doesn't have knowledge for task A, and there's no connection for task A. We also have base level states here, but they're not activated in the beginning for the organizational learning, because in the beginning, we don't have any organizational learning, organization shared mental model. We have only individual mental models, and also we have context states to represent the phases of organizational learning that I will explain in detail later. In the first order self-model level, we have W states representing the weight of connections of base level states. For example, for person B, from task B to C connection, we have these W states from B to C, and this W state represents the weight of this connection. That's why it's able to activate or deactivate or control the weight of this connection, this learning process, maybe we can say that. We have 3 connections for each person. That's why 3 W states for each person and also for organization. And here, there are arrows between W states, inner arrows. What are they? They are, these arrows are for the feed-forward learning. They activate the links between W states of individuals and organization, and they provide feed-forward learning, and they create the shared mental model. And also we have feedback learning arrows from organization to individuals. Meaning of this is individuals can learn from their organization via feedback learning. This is the overall model for our basic organizational learning study. In the second order cell model level, it was for control of adaptation, as Jan said in the beginning. We have H states for speed of connection, speed of learning. M states for the control of persistence of learning and forgetting, of course. And also we have higher order W states to control the weight of connections between W states. These connections are for feedback and feed-forward learning, as you can remember. That's why we can say that these higher order W states control the feedback and feed-forward learning mechanisms. They can activate the links, and they can start the process of feedback learning and feed-forward learning. This is the simulation results, overall simulation results. We can see all the states here, but I prefer to explain them in separate manners to make things clear for you. For example, here we have only mental model states of individuals, and we can see the individuals' mental model states only. For example, in the beginning, in phase 1, this is for this range is for phase 1, the first phase, and this is for individual learning. The second phase here is for shared mental model formation. The third phase is for the feedback learning from organization to individuals. And the last phase is for the improvement of individuals with the help of their organization. Individuals learn in the first phase because it's the individual learning phase. And we can see that one individual learns better than the other, can learn better than the other. It's because of the persistence factor. And we can also see that after learning finished, after learning parts finished, individuals start to forget, and their forgetting rate are also different because not all people are same. After second phase, this phase, we cannot see this phase here because these simulation results are only for individuals, but I can show it here. It was 350, and here in 350, the time 350, we can see the shared mental model formation. These are double states of organization. As you can remember, these double states represents the connection weights of organizational models, mental model, shared mental model. That's why activation of these these double states creates the shared mental model. And we can see that for connection B2C is higher than the other ones because both of our persons have connections from B to C, but for A to B, only person A has connection, and for C to D, only person B has connection. That's why here this double state is higher than the others, the B to C double state. I mean, the learning is better for this task. And after the shared mental model formation in this phase, in the third phase, for the feedback learning, we can see the double states from organization to individuals increase here. That's why individuals start to learn again. And in the last phase, as you can see these jumps, individuals improve their mental model states with the help of their organization. After the feedback learning, feed-forward learning here, after the shared mental model formation, feedback learning starts in this third phase. And also, we thought that we can improve our models by adding some characteristics like context sensitivity. This is our context-sensitive aggregation control model for adaptive aggregation. What is adaptive aggregation? Adaptive aggregation is the selection process of combination functions that will be used for aggregation of individual mental models. For example, shared mental model formation is an aggregation, and we wanted to make this aggregation context sensitive to make our models better. And we add these control states. These C states are for the control of combination functions, selections, and these context states are for control of the context. As you can see here, we have 4 different types of C states, C1, C2, C3, and C4. The meaning of this is we have 4 different types of combination functions to combine the individual mental models. And these context states are again for 3 different contexts. I will explain it soon. These are aggregation control states, as I said, and these are context factors. We have logistic sum function, scaled maximum function, Euclidean function, and scaled geometric mean function. We will choose, actually, the model will choose these functions in terms of the context. It will be context-sensitive selection of combination functions in this model. How did we do it? We have these context factors: knowledgeability, dependency, and preference for type of quantity. For example, if A and B are not experienced, both of them are not experienced, and if they are not dependent, the combination function selection will be a logistic function. model will do it itself. We have Boolean propositions, Boolean functions for these C states, the control states. And this is a simulation example, simulation results for this model, our context-sensitive model. For example, if we have some context states are activated in this phase, that's why the control states, the combination function selections are blue and the red one, mainly in the blue one actually. But after the context change, this is the point of context switch. After this context switch, we can see that combination functions are changed. The selected combination functions become pink one, and the blue one decrease after the change of the context. Actually, we used different parts, different characteristics to model with the self-modeling networks, like this context sensitivity. In our studies, we used multi-level learning with teams and groups. And also, we are also currently working on the effect of leadership on organizational learning. We have been trying to extend our work with these type of different approach, different fields. And for the discussion, I will give the words to Jan. Thanks.